All right, guys, we're going to try this again. Hopefully this time the volume will work. We are going to look at piecewise functions today, starting with the state standards here and the success criteria. Today you need to be able to evaluate piecewise functions, graph piecewise functions, and write piecewise functions. Vocabulary that you need to know. A piecewise function is a function defined by two or more equations. Each piece of the function applies to a different part of its domain. So we are going to be talking about domain a lot today. All right, a step function is a piecewise function defined by a constant value over each part of its domain. You can see here in the picture, a step function gets its name from what it looks like. It looks like a step. So each one of these is a constant function over a certain part of the domain. Example 1, evaluating a piecewise function. All right, to evaluate a piecewise function, first you have to understand that the piecewise function, so it has two different functions. The first function, 3x plus 1, is only defined for x less than 2. And the second function is only defined for x greater than or equal to 2. So it's a function because it still passes the vertical line test. So it's important to also remember what a function looks like, because when we're looking at the graphs, that's important. Here's an example. In the key idea, you can see if you use the vertical line test, this comes up to 0, has a solid circle. At x is 0, it has an open circle. So even though it has 2 points, because this one's open, it still passes the vertical line test. So each one of these we're looking at, these are considered functions. All right, so to evaluate a function, we simply have to decide which function to plug x into. All right, so x equals 2. This says x less than 2, so we don't even worry about the first part. So x equals 2 will go in the second function, because x greater than or equal to 2, that's the part of the domain that we're looking at for a part. So for a part, we're going to say x minus 5 is the function. So we've got x minus 5. Now it's saying let x equal 2. So 2 minus 5. 2 minus 5 is negative 3. So we can say f at 2, because when x, right here, f of x, when x is 2, that equals negative 3. All right, now we're going to look at b part exact same way. So x equals negative 1/3. Is negative 1/3 less than 2? It is. So we're going to plug it into the first part of the function. So the first function is 3x plus 1. Now we're going to plug negative 1/3 in for x. So we're going to have 3 times negative 1/3 plus 1. We can write any number as a fraction by putting it over 1. So that reduces and becomes negative 1 plus 1, or 0. So in the same way, we can say f of negative 1/3 equals 0. All right, we're going to do the same thing for the next function. We have h of x equals negative 3x. That's defined for all x's less than 0. And we have 2x plus 7 if x is greater than or equal to 0. So this time it gives us several values for x, and we're going to plug those in one at a time to figure out what it would equal when we plug it in. So let's say, what is h of negative 6? Negative 6 is less than 0, so we're going to plug it into the first function. Negative 3 times negative 6, and that equals 18. And then we're going to do the second one. So let's do h of negative 1. Negative 1 is also less than 0, so it's going to go into the first function as well. So we're going to have negative 3 times negative 1, or 3. All right, the next one is 0. So let's look at h of 0. 0 is not less than 0. 0 is greater than or equal to 0. So we're going to use the second function here. We're going to use 2 times 0 plus 7. 0 times anything is 0, plus 7 is 7. So h of 0 equals 7. All right, now we're going to look at h of 5 halves. 5 halves is another way to write 2 1/2. All right, so 5 halves is greater than or equal to 0. So we're going to use 2 times x, which is 5 halves in this case, plus 7. Again, we can write any number as a fraction by putting it over 1. So the 2's reduce. 5 over 1 is just 5. 5 plus 7 is 12. All right, the last one, what is h of 4? All right, 4 is also greater than or equal to 0. So see, the first thing you have to do is figure out which one you're even looking at. This is a piecewise function. There's 2 pieces to this function, and then you plug it into the function based on which part of the domain makes it true. So h of 4 is greater than or equal to 0. So we're going to do 2 times x, or 4, plus 7. So we're going to have 8 plus 7, or 15. All right, so you do have a key idea right here where it says piecewise function. A piecewise function is a function defined by 2 or more equations. So 2 or more, it can be more than 2, but both of these that we have looked at had 2 parts to the equation. And each piece of the function applies to a different part of its domain. An example is shown below. The expression x minus 2 represents the value of f when x is less than or equal to 0. So this one right here, this is your x-axis. This is x at 0, so this is less than 0. The expression 2x plus 1 represents x is greater than or equal to 0. So it has to go to the right of the y-axis because that is your x at 0. All right, I really enjoy piecewise functions. I think they're fun, they're interesting to graph and to evaluate because you have to look at it and you have to truly understand the domain. So hopefully this will help you kind of understand what the domain does even more than in the past. All right, the next thing is a self-assessment. It says evaluate the function when x is these different values. So I want you to pause the video, take a few minutes and see if you can choose which part of the domain that these numbers go to, and then plug those into the function or the piece of the function that it applies to. When you've taken a few minutes to do that, you can start the video back and we'll check your answers. All right, hopefully you've taken a few minutes to do those on your own, and let's check them. So f of negative 6 goes in the first function, so that one equals 3. That is just a constant function, so it's just 3. F of negative 1 fits in between negative 1 and 5, so it goes in the second piece. So you've got negative 1 plus 2, or 1. 0 also falls in between negative 2 and 5, so you use the second piece. 0 plus 2 is 2. And then 5 halves. 2 1/2 falls in between here as well. So again, we're using x plus 2. So 5 halves plus 2, that's the same as 4 1/2. Or if you left it as a fraction, 9 halves would be your answer. All right, f of 4 also goes in the middle piece. 4 plus 2 is 6. And that's your final answer. So as you can see, we evaluated the function at these different x values. None of them were greater than 5, so we didn't use the last piece of the function to evaluate any of those expressions or equations. All right, example 2 says graphing a piecewise function. So we've got a graph, y equals, we've got negative x minus 4 for x less than 0. So here's our x at 0. This is our x-axis, remember. Everything to the left of 0 is less than 0. Everything to the right of 0 is greater than 0. So we're going to graph this piece of the function on the left side and this piece of the function on the right side of the y-axis. Then we need to describe the domain, the range, and the end behavior. All right, so negative x minus 4, this is a linear equation in slope-intercept form. So we know that this is our y-intercept. So we can go down to -4, 1, 2, 3, 4. The domain says x less than 0, so we know we're going to have an open circle. That point is not included. And we're also going to have a -1 for our slope. So if we go down 1 over 1, we're on the wrong side of the graph here. So we want to only graph when x is less than 0. So we only want to go left of this point. So to have a negative slope, I'm going to have to rise 1 and go backwards 1, rise 1, back 1, and so on. So I can graph that. All right, so that is the first piece of that function graphed. Now let's graph the second piece. The second piece says x, just x. That means it has a slope of 1 and a y-intercept of 0. This time the y-intercept can be included. So we can say this is a solid circle. So I'm going to graph that. And then I got a slope of +1. So up 1 over 1, up 1 over 1, etc. Hopefully you remember graphing linear equations from Algebra 1, and this is just a refresher. The only difference is now we're looking at kind of combining, putting pieces together. All right, so now we have graphed the piecewise function. Now we need to describe the domain, the range, and the end behavior. So the domain is talking about the domain of the piecewise function. So we've described the domain of individual functions before, but now we have separate pieces together. So this one starts at x at 0 and goes left forever. This one starts at 0 and goes right forever. So the domain is going to be all real numbers, or -infinity to infinity. All right, the range includes all your y values. Your y values are everything on the y-axis. You can see this one starts at -4 and goes up, and this one starts at 0 and goes up. So we're going to start at the lowest piece, and we're going to say all y's greater than 4. Now, if this were a closed circle, it would be greater than or equal to, but because this is an open circle, this one is strictly greater than. And then our end behavior, is defined as x goes to -infinity and x goes to +infinity. So basically we're saying, what do our y's do when our x's go to the left? Because this is x at 0. When you go to the left, that's going towards -infinity. My y's are going up. So my y is going to the positive infinity. And then what happens on the other side? So this says when x approaches infinity. So when x is going towards the positive side, when x is going positive, you can see the arrows going up. Y's are also going up, which means it's approaching infinity, because those arrows means it's continuous. It's not going to stop. All right, that's all for that one.